Okay, so we talk about generating better machine code with SSA, and this is not the Social Security Administration and I pair programming machine code. What I'm actually talking about is a technique used by most modern compilers to generate better machine code, and it's called SSA. And I'll get into all the stuff about SSA, what it is, and how we use it. But I'd like to start by talking about how we got here. We got here starting with the Go 1.5 compiler. And let me just describe what the Go 1.5 compiler is. It started out as the Plan 9 C compiler back in the 90s. And that was the basis from which the Go compiler, the whole Go project started. Russ and Rob and everybody took that compiler and modified it so that it could compile Go instead of C. And then in the Go 1.5 compiler timeframe, that code base of the compiler, which is also written in C, was auto-translated to Go. And so as we were developing Go 1.5, I was working on things like maps and other runtime functions, and I was looking at why certain things were being slow. And so as part of that, I'm looking at assembly code that the compiler is generating. And so here's an example of a chunk of assembly code that the Go 1.5 compiler generated. So it does a move from register AX to BX. It does a shift on register BX, and it stores it to memory, and then it calls a function. And I was looking at this, and I'm just thinking, why is that first move there? It seems kind of silly. You'd much rather just do the computations directly on that original register instead of moving it first. There's no point in that move. All the registers die at the call anyway. So it sort of puzzled me as to why the compiler did this. And so I took a couple minutes to look into why were these 4 instructions instead of 3 instructions. And so I looked at the compiler, and I tried to figure out, well, how can I fix this in the compiler? And it turns out that this was kind of a hard problem to fix in the compiler. The way the compiler is currently written, it was a very difficult job to patch in a fix to this problem. And so I sort of put this on the back burner and said, maybe we'll get to this at some point, a more comprehensive fix for this. And then a couple days later, I was looking at some more assembly code, and I came across this instruction. This is a multiply by 16 as a multiply instruction. And multiply instructions for hardware are fairly expensive instructions. They take multiple cycles to run. Why not just do this with a shift? A shift by 4 is totally equivalent to a multiply by 16. And this is another sort of piece of the puzzle, like why is the compiler doing this? Why isn't it just using a shift? And I looked into it with the compiler, and this is actually a pretty easy fix to the Go 1.5 compiler to make it do this optimization. But before I even got around to actually doing that, I came across yet another example of where the compiler is doing something kind of silly. It's writing a register into memory, and then it's reading that value straight back out of memory again into another register. Why don't we just use a move instead? Here's another example I came across where we're computing something into one register and then moving it to another. Why don't we just compute it into that destination register to start with? And as I was looking more and more at what the generated code looked like, I found more and more examples like this one where there's a compare, it's not needed. Here's another example where you're moving things into a temporary register and then to another register instead of just moving it directly. And at this point, I was getting frustrated with the quality of the code generated by the Go 1.5 compiler. And so as part of that frustration, I decided to claim that we could totally do a better job than the current compiler's doing. We could make the code 20% smaller and 10% faster. And I sort of made up these numbers, totally with no evidence whatsoever that this is actually possible, just sort of my anecdotal evidence looking at compiled code. And so I made a proposal. Here's how I'd like to fix the compiler to make it better. Instead of sort of going through and fixing all those problems one by one, let's do something more principled that maybe fixes all these problems all at once. And so what I put in my proposal is I'd like to fix the current compiler. I'd like to convert it from a syntax tree representation into an SSA-based representation. And once we do that, then we can implement a lot of optimizations that are difficult to do in the current compiler, but would be easy with this new representation. And there's a whole lot of jargon in there which I haven't explained yet. I haven't explained what a syntax tree is. I haven't explained what an IR is. I haven't explained what SSA is. I'll get to all of that. But first, I'd like to tell you a little bit more about how this project happened. So the timeline started with me mailing a proposal to Golang dev saying, hey, I'd like to rewrite the compiler. This proposal was contained those quotes I showed you earlier and was sort of intended to get buy-in from the rest of the Go community about whether we should do this, if we do it, how we do it. And there was pretty positive feedback about the proposal. And so on March 1st of that year, we created a branch to start actually writing code for this project. And it took about a year to rewrite the compiler to use this SSA stuff to generate better code. And so we eventually merged back into the master branch exactly 1 year later. The code was now good enough that we decided to put it on master, and then it got released in Go 1.7 for the AMD 64 backend. That's the Intel AMD processors. And then for Go 1.8, that SSA backend was ported to all the other architectures that we support, the 386, ARM, MIPS, PowerPC, IBM, all in Go 1.8. And so let me just show you what kind of performance we get with the new SSA backend. The AMD 64 version, as I said, launched in Go 1.7. It was about 12% faster on the Go 1 benchmarks. It's not a very good benchmark set, but yet it's sort of what we have, and so that's how we measure our compiler performance today. And it generates 13% smaller code segments. So the code is both faster and smaller using this new compiler. You can see here the distribution of the performances across the different benchmarks in the Go 1 benchmark suite. And you can see that some actually get worse, and some get 25 or 30% better. So there's sort of a wide range depending on how good the optimizations in the new compiler can handle your code. But in general, we get quite good speedups. The speedups are even better on ARM. So the ARM compiler, which launched in Go 1.8, we make the average program 20% faster and use 18% less code. And you can see from the distribution of benchmarks here that some of them get up to 50% faster. That's like a factor of 2 faster in runtime than using the old compiler. So in addition to this sort of not very good benchmark suite that we measure everything against, after we launched, we got a whole bunch of experience reports from people who actually use this code in production. So we had people with big data workloads who were getting 15% improvements. Someone had a convex hull application, which does a lot of floating point, and they got a pretty substantial improvement over Go 1.5. There was someone with a hash function library, which got almost 40% improvement in their runtime. And there was an audio processing application that on ARM got almost a factor of 2 improvement in runtime. So we see not only that we have better performance on sort of our synthetic Go 1 benchmarks, but on real-world applications, we also see similar improvements. So that's always nice to see. So, of course, we're adding new work for the compiler to do, so we want to make sure that we don't make the compiler a whole lot slower. One of the nice things about the Go language is that it has a very fast compiler for fast iteration during development. And so we're always concerned as whether we're making the compiler faster or slower. And it is true that we're adding work for the compiler to do, but we're also compiling the compiler with a new compiler, which makes the compiler faster. So it's hard to get your head around sometimes. But I'd like to poll the audience. What do you think? Do you think the new compiler is going to be faster or slower? Which of these effects do you think is going to win out? So I'd like everyone to raise your hand if you think the new compiler is going to be faster. And how many people think the new compiler is going to be slower? Okay, like more people think it's going to be faster. Well, it turns out that you're both right. For AMD 64, the new compiler is about 10% slower. So all the extra work we're doing to generate better machine code is not quite eliminated by the speed that we make, the increase in speed of the compiler by compiling the compiler with itself. But on ARM, it's actually the other way around. For ARM, the compiler not only generates better code, but the compiler is faster because the better code is being used by the compiler. So you can see that there's sort of this tension between implementing new optimizations to make the compiled code faster and the time it takes to actually run that in the compiler. Those two things sort of, for the most part, cancel out in the compiler that we built. So I've told you a little bit about how we use the SSA compiler and what its effects are, but I haven't really told you what it is yet. So I'd like to tell you what SSA is. For now, it's just a 3-letter acronym. Why is it useful? And how does Go use SSA to make better code? And I'm actually going to start with number 3 there. So here's the 30,000-foot view of what a compiler does. The compiler takes your Go code as input and generates an object file as output. And so the input to the compiler is a UTF-8 text file. The output is an object file, which basically just contains, it's a container for assembly instructions, effectively. And that's what the compiler looks like from really far away. But if you actually get down and look inside the compiler, it's not this big monolithic program. It has a bunch of components to it, and those components talk to each other in some sort of processing pipeline. And the things that the compiler sends from one part of the pipeline to the other are called intermediate representations. So they're sort of in-memory representations of your Go code. And so the compiler just sort of passes those intermediate representations through all the processing phases of the compiler until it gets to the end and generates an object file. And so that's what IR is in this quote. So we're converting from a syntax tree-based intermediate representation to some other intermediate representation. And so in order to sort of tell you what's going on there, I need to tell you what the Go 1.5 compiler does. And so it takes your Go code as input, it parses it, and then it uses what's called a syntax tree to represent your program in memory. And all the phases of the Go 1.5 compiler used a syntax tree as the sort of lexicon to talk from one phase of the compiler to the next. And so each phase of the compiler takes a syntax tree as input and generates a syntax tree as output. Except for the sort of last phase where we do code generation, and there the intermediate representation is an in-memory version of assembly code. And so for the most part, the Go 1.5 compiler just uses syntax tree as its internal representation. And so let me show you what a syntax tree is. So here's a simple function. It just writes 10 zeros to a slice. Pretty simple. Here's what the syntax tree of that program looks like. A syntax tree basically has one node in the tree for every piece of syntax that's in your program. So that's why it's called a syntax tree. And you sort of see parent-child relationships between all the parts of the syntax of your function. So a function has a name child and a child which is all the arguments, and a child which is the body of the function. And the body of the function node has all the statements that are in the body as its children, and so on. And so syntax trees are pretty simple conceptually, and that's what the Go 1.5 compiler uses as its lexicon to do all its operations. So the things we do on syntax trees, we do type checking, and that just makes sure that we know all the types of all your variables in the program and that you're not doing any type errors in your program, like assigning a float to an int or anything like that. Then there's a whole bunch of optimizations that the compiler does. We do closure analysis to make sure that we can build closures for functions, internal functions. We do inlining, which is taking the body of one function and inserting it in place at a call site in a calling function. And that's actually really easy to do with a syntax tree. You just sort of paste one tree into where the call node was in another tree. We run escape analysis, which decides whether variables need to be stored in the heap or on the stack, because if we can store them on the stack, it's much more efficient. And then we do things like add temporaries where we need them, introduce runtime calls for operations like map operations or channel operations, ones that we can't do just with machine code, need to call into the runtime for runtime support. And then the last thing that the Go 1.5 compiler does is it generates code from the syntax tree. And this is sort of a big monolithic code generation step that does all the parts of code generation, instruction selection, register allocation, and so on, in one final step. And so I've told you what a syntax tree is. The syntax tree is sort of the lingua franca of the Go 1.5 compiler. And so for the Go 1.7 compiler, we're going to add SSA to this picture. And the way we're going to add SSA to this picture is we're going to keep everything except for the last code generation step. We're going to throw that out, and we're going to do something new in that step. And the reason why we did this is because writing the whole compiler again from scratch is a very big job. It's much easier to sort of take one piece at a time and replace it with something better. And that way, we keep all of the other optimizations that these passes already did. We keep all the type checking and error reporting and everything else that the Go 1.5 compiler is already good at. We only want to make better machine code, so we're just going to sort of replace that last piece. And so here's a picture of what happens to the Go 1.5 compiler when we add SSA to it. We're going to delete that code generation step, and instead we're going to add a whole new set of passes. We take the syntax tree and we convert it to this new SSA representation. Then we do a bunch of optimization passes on that SSA representation, and then when we're done, we take that final SSA representation and we convert that back into in-memory assembly so we can build an object file out of it. So this is sort of delicate surgery of the Go 1.5 compiler. So we're now 20 minutes into this talk, and I haven't told you what SSA is yet, so time to get to that. So SSA is just an acronym. It stands for Static Single Assignment. And what this means is that a program is in SSA representation if there's only one assignment for every variable in the program. And it's static because there's only one assignment in the text of your program. If that assignment is in a loop, of course, that assignment will run more than once. So dynamically, there could be more than one assignment to each variable. But statically, looking at the text of your program, there's only allowed to be one assignment for every variable in the program. So it's a pretty simple concept. Of course, most programs aren't static single assignment, so we have to convert them into static single assignment by a process which uses variable renaming. So here's, on the left, a very simple program. It's got multiple assignments to all its variables, and we want to convert that so there's only one assignment for every variable. And the way we do that is we rename the variables. So for the variable x, for example, we have now two new variables, x1 and x2, which represent what x used to represent, but now there's two different assignments to x1 and x2. And on the right-hand side of all these equations, we now need to decide, there was an x, do I now use x1 or do I use x2? And so you can sort of imagine an algorithm that goes through and figures out what variables I need to use on the right-hand side corresponding to what those variables used to be in the multi-assignment program. And so it's a pretty simple conversion for straight-line code like this. It gets more complicated when you have branches. And so imagine a program like this on the left, which has two assignments to x. When we convert that to single assignment, we now need two different variables we're assigning to, x1 and x2. But then at the end, when I want to print x, which value of x do I print? I can't print x1 or x2. I need to sort of print one or the other, and I have no way of deciding a fixed number to put in that spot. And so the answer is there's a new operation called a phi function in SSA, which represents the merging of two different values. And so at any merge point where control flow merges, if there's two different values that need to be merged, we have to introduce this phi function, and it generates a new value, which we can then use subsequently. So here we've introduced x3, which is the merge of x1 and x2, and then beyond that point, we can then use x3 for whatever the original value of x was. And so these phi functions sort of represent explicitly what was implicit in the original program. And with that, that's basically all you need to do to make SSA code out of regular code. And so here's our example program again. I've converted all the assignments to SSA form, so there's only one assignment for every variable. And in addition, I've embedded all the assignments in this program into a control flow graph. And the control flow graph are these boxes. Let me just show you those individually. So each box sort of represents a chunk of instructions that all execute together. And you can sort of see the control flow with the arrows. So you block the top, then unconditionally flows to the middle block, and that has a conditional in it, so that may go one of two places. And this control flow graph gives you a better understanding of where code flows in the program, as opposed to a syntax tree where it's not really representing control flow. The arrows are representing sort of syntax containment. These arrows are actually representing jumps in your program. And so I've now explained to you what SSA is. SSA is this control flow graph with instructions in it for which there is only one assignment for every variable. And so I claim that when we use a SSA representation in the compiler instead of a syntax tree, we can do a lot of optimizations that are difficult to do with a syntax tree. And so let me just explain what some of those optimizations are. Oops. Here we go. So SSA enables a whole bunch of new optimizations that were hard to do in the old compiler. The first is common subexpression elimination, and that means that if I compute some value twice during my program, instead of computing it twice, I would rather compute it once and remember the result, and then I can just use that result again later in the program. I don't have to recompute it. Dead code elimination gets rid of code which is otherwise unused. Dead store elimination gets rid of stores that are immediately overwritten by another store. And this happens quite a lot in Go code, where you declare a variable, and that variable sort of automatically gets assigned the 0 value, and then you assign a real value that you actually wanted in that variable next. And we'd like to, when possible, get rid of that first 0 assignment. Nil check elimination and bounce check elimination. Go requires that we panic if you dereference a nil pointer or if you access an array out of bounds. And so there's a lot of checks in Go code that are required to make that happen, but often we can prove that those checks aren't needed. They're never going to fail. And so in those situations, you'd like to remove those checks. Register allocation, we'd like to do a better job of deciding what registers to use in which situations and avoid a lot of the register moves that you saw early in the talk. You'd like to figure out the right order of instructions and a whole bunch more. And so let me just go through a few of these and show you why SSA is sort of the right representation in order to do some of these optimizations. So first, common subexpression elimination. Suppose I had a program that had x plus 5 twice in it. And I'm wondering, can I just reuse the value, the result of the first x plus 5 instead of recomputing it later? And so if I have a syntax tree, the answer is, well, maybe I can reuse it. I have to sort of look through all the code that's in between those two statements to see if there's any other assignment to x. Because if there's any other assignment to x in that chunk of code, then I have to redo x plus 5 because x may now have a different value. So it's sort of complicated, and in order to do this optimization in a compiler that's based on a syntax tree, you actually have to look through a whole bunch of code just to do one little optimization. Whereas in SSA, we know that there's only one assignment to x, so that this optimization is always OK. I don't have to look through that code that's in the middle there. I know that x only has one value, and if I computed x plus 5 before, I know immediately the answer unequivocally is yes, I can reuse that value of x plus 5 again later. And so this makes implementing common subexpression and elimination a whole lot easier in the compiler, because we have this only one assignment property. Same thing for dead store elimination. If we have a store of 0 to some location, and then later on I store a 1 to that location, can I get rid of the store of 0? Is it necessary? And there's a whole bunch of things I need to check to make sure that that's a safe thing to do. I have to check that p hasn't changed in value between those. I didn't reassign p. There's no control flow that sort of jumps out of there before the assignment to 1 happens. And I have to make sure that there's no reads of that location in that code as well. And SSA actually helps with a lot of this also. SSA sort of automatically gets us the fact that p hasn't changed between those two statements, because I know there's only one assignment to p. It must have been before the p equals 0 assignment. So I know that p hasn't changed. The control flow graphs gives us an easy way to determine whether any control flow exited without also executing the p equals 1 statement. And the fact that we need to check to make sure there's no reads of anything of p in the middle of that chunk of code there, we still have to do explicitly in the SSA compiler, but we've sort of eliminated 2/3 of the work that we have to do in order to make this optimization work. Similarly for bounce check elimination, here's a chunk of code where we check to make sure that the length of the array is big enough, and if so, we read the third element out of the array. And we know that that bounce check is never going to fail. We know that the array is big enough, but in order to remove the bounce check, we sort of have to prove it to ourselves in the compiler. And the way we do that is we know that we check the length of A and see whether it's at least 4, and then we do this bounce check to make sure that the index we're accessing is in bounds. And we can only remove this bounce check if we know that A hasn't changed in between these two statements. And the way we know that A hasn't changed between these two statements is that there's only one assignment to A in the whole program, and so it can't have changed in between those two statements. And so we can go ahead and delete those two blocks altogether and all the code that's in them. They're not needed. We know that the bounce check is going to pass, and we can bypass that whole check and the panic. We don't have to generate the code for it, and so on. So in addition to all these sort of big optimization passes like common subexpression elimination, we also have lots of small things that we'd like to do. So for instance, a small optimization might be if we ever see x minus x, we know we can just replace that with 0. And so we use what are called rewrite rules to encode a lot of these sort of small optimizations in the compiler. And the compiler contains a rewrite rule application engine that takes all these rewrite rules and your code and finds all the places where these rewrite rules apply and applies them to your code. So here's a very simple example. If we have a subtract, 64-bit subtract of a value with itself, we can just replace that with the constant 0. And we have a whole bunch of optimizations like this in a big rewrite rule file in the compiler. This didn't format quite correctly, but no worries, we'll figure it out. So if we have a multiply of two constants, we'd like to replace that with just the result of that multiply. And so we have a rewrite rule that says if you have a 64-bit multiply of two constants, you can just replace that with a constant, which is the product of those two arguments. If we have a multiply by 16, we can reduce that to a shift by 4, and here's the rule that does it. If there's a multiply of x by a constant, and that constant is a power of 2, we can replace that with a left shift operation. And similarly, there's other ones you can't read because the formatting didn't come across. But we can replace a not of an equals with a not equals, and we can replace x plus y minus x with just y. And so rewrite rules are used for these small optimizations. They're also used in a pass called lowering, which takes machine-independent opcodes, like opcodes for Go, and replaces them with opcodes for the architecture that you're compiling to. So for instance, in this case, the opcodes on the left are Go opcodes. They're the ones that are written in lowercase. And the opcodes on the right are opcodes for AMD64. They're actual machine instructions. And so we have a bunch of rewrite rules that take all of the Go operations and rewrite them to machine operations. So an add 64 gets replaced with an add Q, which is the 64-bit add on AMD 64. And similarly for equal actually takes two instructions to implement. You have to do a compare of your two arguments, and that sets the processor flags, and then you have to use a separate instruction to extract out the equal bit from those processor flags. And so we have a whole bunch of rewrite rules that do this pass. And the rewrite rules can get pretty complicated. So there's not just these sort of simple arithmetic operations for which we use rewrite rules and the lowering for which we use rewrite rules. We also use them for very big things. This rewrite rule looks pretty complicated, but let me just tell you what it does, is it takes two 8-bit loads and replaces them with one 16-bit load, if it can. And so this rule sort of checks all the possible conditions under which this rewrite rule can apply, and if so, it does the rewrite and uses one 16-bit load instead of two 8-bit loads. The other nice thing about rewrite rules is it makes new ports easy. So say you wanted to port Go to a new architecture. All of the SSA passes are architecture independent. The bounce check elimination works for any architecture. The common subexpression elimination works for any architecture. all you need to do to port to a new architecture is write the lowering rules that tell you for each Go operation what processor opcode you need to use. And so it took a year to write the SSA backend because we had to write all these optimization passes. But it only took a few months to write the SSA backends for all the other architectures. So there are 10 or so other architectures. We did them all in just a few months. And if you look at the rules files for all these architectures, they're 1,000 lines-ish. So with 1,000 lines of code, there's some other stuff you have to write too, but the bulk of it is the rules you have to write to decide for each Go operation what processor-specific operation you need to use. And so we were able to do all that work just in the 1.7 to 1.8 timeframe. So just sort of to sum up here, converting the compiler to use an SSA IR instead of the old syntax tree IR led to substantial improvements in generated code. We got 12% improvement on AMD C4 and 20% improvement on ARM, and similar improvements in code size. And so we have a lot still to do. We've sort of launched these compilers. We have some more work in improving optimization passes in 1.9 that will be coming out shortly. And then there's an infinite amount of additional optimizations we're looking at. So we're looking to do things like alias analysis, which goes through and figures out in your code where pointers point to, and can they possibly point to the same place, or do they always point to different places? And using that information, we can do better optimizations, like store to load forwarding. If you store something to a pointer and then load from it later, can we just pass that in registers instead? And with better alias analysis, we can do a better job of doing that optimization. We can do better dead store removal if we know certain pointers don't point to the same place. We can do things like devirtualize interface calls. So you can do a direct jump to where the interface call goes if you know what the type of that interface is. And you can figure out the type because you know where that pointer came from. We'd like to do better register allocation. The register allocator that we have in the Go compiler today, I would give it like a C grade. It sort of does a reasonable job for straight line code, and it's in branching code, it doesn't do so great a job, and we'd like to see improvements in the register allocator. We'd like to do better code layout, deciding in what order we write down the instructions. We'd like to take all the code that, for instance, we'd like to take all the code that we expect never to execute because it's the panic that happens after a bounds check, and we expect bound checks to never fail, approximately. We'd like to put all that code somewhere else away from the mainline code so that the instruction cache works better. We'd like to do better instruction scheduling of deciding what instructions go where. We'd like to take code that's in a loop and move it out of a loop if we can, because then it only executes once instead of a whole bunch of times in the loop. And we're looking at ways of deciding how we lift code out and whether it's worth doing. But there's a big caveat to all this additional work is we don't want to ruin our compile speed. So we really only want to do optimizations if we can ensure that we can do it quickly in the compiler and that it has demonstrated benefits for real programs in the real world. And part of that is a call out to everyone here is we need benchmarks. The Go 1 benchmarks really do kind of suck, and we'd like to have a better set of benchmarks. So if you have ideas, if you have kernels or whole programs that you think would make great benchmarks, please get in contact with us because we need a better benchmark suite to decide whether optimizations that we do in the compiler will have real-world implications or whether they only help one silly benchmark that we happen to have already. So I think that's about all. I'd just like to give a really big thanks to all the people who helped out in developing the SSA compiler. There were some people at Google who worked on it, but a sort of majority of the work happened from people just in the community, helping out with a port to PowerPC or implementing some particular optimization phase. It was a job of the community, not just a job of the core Go developers. So I'd like to give a big thanks to everyone who helped out.